In this video, I'd like to discuss two concepts which are essential in control theory: feedback and feedforward. You're probably familiar with feedback because it has become part of the popular culture in recent years or even decades. It is more unlikely, however, that you've ever heard of feedforward. If you Google both words, you get 175 times more results related to feedback than feedforward. And the word corrector tells you that feedforward is a word that doesn't exist. So unfortunately, something similar happens in control theory. Feedforward tends to be overwhelmed or shadowed by feedback, and many books don't even mention the concept of feedforward. So here we don't want to make the same mistake because many real control applications do use both concepts, and not only control application, even human action can be sorted according to these two categories. Any purposeful action, either if it's carried out by a machine or a person, can be sorted according to them. So what are their main characteristics? I'll use this here. Feedback is essentially anticipative. No, sorry, it's the other way around. Feedforward is essentially anticipative. It acts according to previous knowledge. Previous knowledge. That is, it acts according somehow to a plan. It doesn't wait until things go wrong. It doesn't wait. Whereas feedback is always reactive. It seeks to correct something which is wrong. In some way, it's always too late. Something must be wrong, and once it's wrong, feedback starts acting. So I'd like to dwell on these ideas by using an everyday example. Imagine that you've been told to make dinner, but you happen to be a lousy cook. So you have to look up a recipe in a book, maybe watch some YouTube videos, or ask someone you know that knows how to cook. In all these cases, you're looking for instructions, something telling you what to do. So let me draw here a box representing the process of making dinner. The box, in the box we have the cooker. Here's the cooker, and maybe I don't know, a pan. And since you don't know how to cook very well, you choose a simple recipe, maybe some rice. So the recipe is simply a set of instructions on what to do. We know we need some rice, some water, and a pinch of salt, but we cannot put them or dump them into the pot randomly. You have to follow the right sequence, and that's what here we could represent through signals. We're already familiar with signals. So the right signal for the rice, for the amount of rice we add, could be For example, like this, all rice is added at the beginning. This is rice. We have also to add some water, maybe this amount of water, and a pinch of salt, maybe at the end, maybe at the beginning. I don't know, salt. The salt could be added right here. This is the time axis, by the way, time, and time. So each one of those is an input for the system. We also need, of course, some heat, and again in the right order. We have to turn on and off, rise and lower the heat of the cooker. So maybe this could be the sequence of the heat Q, and that's also an input for the system. As you can realize, the inputs are not just material things. Well, one of the inputs is a wave of energy. So the outputs are what you're interested in. So, for example, it could be the smell of the rice, the smell, its taste. Its taste is an output of the system, and maybe its tenderness. So we can have a bunch of outputs, by the way, in this case quite difficult to measure. But what the recipe tells us is that if you follow the instructions in the right order, well, the smell, I don't know, will go like this, and this is like the optimal point. Its taste will also go up, and this is the good point, and its tenderness will be like this. And if you overcook then the tenderness will go to up, and then you won't like it. So if you follow the instructions, you will eventually get to the point at which you want to arrive. Now let me ask you, will you succeed if you follow rigorously all the instructions and forget about anything else? Maybe you will, but maybe not. And this is something that people keen on cooking know very well. But why is it so? Well, maybe because the pan you're using is not the same pan as the one that the guy who wrote the recipe used. Maybe the cooker is not the same either. Maybe the brand of rice you're using is a different, or even its breed, the water. I don't know. There may be a blackout in the kitchen, and then your heat supply cuts for a while, or maybe I don't know. The children turn off the cooker accidentally, and you have to go. So there's a lot of things that can go wrong. You could also accidentally drop too much salt on the water. So many things. And for those reasons, you always have to keep an eye on the kitchen, and that is what we call feedback. In an ideal world, we would never need feedback. If you had always the same ingredients, and you perfectly knew your cooker, and your cooker was perfectly reliable, you could cook blindfolded without tasting or smelling or checking anything you're doing. But unfortunately, this is hardly the case. Not only in this simple example, but in every system. You have the same phenomena. In particular, here we're talking about two different phenomena called disturbances and uncertainty. All those examples of something going wrong were disturbances and uncertainty. We'll define them rigorously in due course. For now, it suffices to say that uncertainty refers to the fact that all systems change and you can never get to know them perfectly. This is uncertainty. So therefore, all plans you make according to your knowledge are flawed in a way from the outset, at least partially. Disturbances refers to other outputs apart from the ones you can manage. They affect the output, but you never really know perfectly when they appear, nor their intensity. So it is to alleviate these effects, these two forces of control system, that we always or almost always need feedback. Because thanks to feedback we can change our course of action. However, feedback is not free of drawbacks either. Whenever you use feedback, you need to rely upon the information which is provided to you by a device called a sensor which is represented by these dots here. Obviously our sensors are the senses. So based on the information supplied by the sensors and according to what we expected from the plan, according to this information, the decision maker, or as we shall call it, the controller has to make a decision and act upon the inputs of the system. But sensors can lie. Sensors can be deceptive. Imagine, for example, I'm cooking for you and I have a problem in my taste buds. Something tasting good for me will be awfully salty for you. And the analogy also works, for example, if I've been smoking while cooking. In those cases, some other signals are interfering. I can draw them like here. Some other signals are being added here, are interfering with the outputs, and those signals are called, I need some space here, are called noise. And in both cases it is very consequential, because I'll be making decisions, the controller will be making decisions based on faked or at least biased measurements. And the question is that, just as with disturbances and uncertainty, noise cannot be prevented from arising. There's always noise in every feedback scheme, and we have to learn how to deal with it. So as a consequence, if you trust your model, you have a model and it is reliable. If you trust it, if you think what you know about the system is quite good, you can stress feed forward. The less you trust the model, the more, if the model is not very good, the more you'll have to stress feedback. But at the same time, the more sensitive you'll be becoming to the deceptions inherent to any measurements. So to wrap up all the ideas, let me draw the following scheme. Here it is. In principle, feedforward should be enough to govern a system, but since there are always disturbances and uncertainty, you need to resort to feedback. You have to overcome the limitations of feedforward schemes, that its sensitivity to uncertainty and disturbances. But feedback itself has some limitations. It makes the system sensitive to noise. Well, the art of controls theory because at all times the control action is a combination of these two. The art of control theory is the art of striking a balance between these two limitations, this one and this one, in conjunction with the objectives that you're pursuing. And that is what we'll learn to do in this course.